Great. So now we'll look into how we can use SQLancer to find bugs in historical versions of database systems, right? Because if we run SQLancer on the latest version of the systems, it's very likely that we won't be able to find any new bugs. Specifically, we'll look into how we can find bugs in SQLite, right? So if I build now SQLancer on the latest version, we'll see that we won't find any new bugs in it, right? So I'm now executing SQLancer on SQLite using the NOREC oracle. And we'll quickly see that there are no bugs being found, which is indicated here that 0 threads are down. And we can also not see any indication of bugs being found. So in order to find now bugs, we'll need to change the version of SQLite. And given that SQLite is an embedded database system where the binary of the database system is included directly in the JDBC driver, so the Java driver that interacts with the database system, we just need to update the JDBC version. So I'm stopping now using Control-C. And now in the SQLancer directory, we can see this POM file here, which will open. And there we now need to search for SQLite. And we need to update the version string. Now, what version should we update or should we change? For this, we can search online, right? What are the available Maven repositories and where can we find a suitable SQLite version? And here, now I already know that we started our testing efforts around 3.27. So now for this, I will just use this version 3.27 to 1 for demonstration purposes. And so 3.27 to 1. Saving. And now importantly, I need to execute a Maven package again to so that the changes are reflected, right? That Maven configures the correct JDBC driver. Right, now we can run the jar again using the same database system. And what you quickly see is that some issues pop up, right? Perhaps here, most significantly, what you can see is that the JVM actually crashed, right? Because given that SQLite is written in C, it can happen that if SQLite has a bug that it might cause a buffer overflow and out of bounds access, perhaps a use after free error, and this causes the whole process to crash. And given that the JVM runs in the same process, this also causes the JVM to crash. This is not, for example, the case with client-server database systems like MySQL or MariaDB, where only the server process crashes and the JVM keeps running. Right, so you can see this, and you can also see other errors appearing. So here, for example, there's another kind of error that SQLancer can find, namely some unexpected internal errors. Here, for example, this error indicates that the database disk image is malformed, meaning that basically the database system here is corrupted. So let's now try to reproduce some of the bugs. But in order for this to happen, we need to find the log directory, which is created in the current directory. Right, so now I will just open the logs directory here. And we can see now that there are some files without this cur suffix. Right, for example, this one here. And here we already have one example where the database disk image is malformed. Right, so this one bug that we detected by executing here an integrity check on this virtual table, which here is a special table. It uses some extension that SQLite provides. So you don't understand exactly what the bug is about, but now let's try to reproduce it. Right, so we have here the complete test case to reproduce the bug. Now we basically need to configure SQLite. So the steps here are, of course, very specific to the database system that we're testing. So SQLite, for example, uses Fossil as a kind of Git equivalent, right, for repository management and for version management. So here now I need to find the same version that we found the bug in, which is version 3.77.2. So here we need to use some fossil specific commands, which I think is fossil tag list. Yeah. And then we can see here all the tags. And now we need to find the right version, 3.27, 3.27.2. We can also actually check out individual commits, but here we already have the matching version, right? So we use fossil checkout and then version 3.27.2. Now things already become a bit tricky because now we are using a FDS 5 extension, and by default the JDBC driver that is being distributed already has this extension. But if we configure SQLite now for building, we actually explicitly need to enable it. Right? So there, if I use tab now, I can already see some options that I can enable. So here I use this FDS 5 to enable it. And in case we need it later, I will also enable the R3 extension. I'm configuring it. Next, I'm using make to build the project. Then we need to wait a while until SQLite is compiled. Okay, now we have SQLite compiled. And what we do now is we try to reproduce the bug, right? So we actually, first of all, we see that we somewhere have the SQLite binary here. Right, so we're now starting it. Basically, the command line interface to SQLite. You can also see that we have the matching version. And now I will, first of all, copy the bug-inducing statement here and append it here. And now I'm copying the whole test case here. And so just pasting it for now. And now you can see that actually we still trigger this bug, right? Database disk image is malformed. So the integrity check here failed. Great. So what would be the next step now? Next, we would need to reduce the test case, also check, for example, if the bug is already known or not. And for now, while SQLancer provides automatic way for reduction, an automatic way, and also we can use external tools like, for example, CReduce. Here, for demonstration purposes, I will just show you how we could reproduce the bug manually. Right, so here we know that the bug-inducing statement is the integrity check, and basically we know that as long as we still see this error, we can further reduce the test case. Right, so let's do this now. We can just take some statements here and remove them. Now I copy everything, paste it again, and execute it. And actually we can see that the bug no longer triggers, right? The integrity check now no longer triggers. So what I do now is I will undo again what I removed, and I will take another bunch of statements that I will remove now. I'll copy everything, start again first of all, and paste. Okay, the integrity check again fails. So again, this also doesn't work, right? So again, undo the change. So perhaps let's remove fewer statements at the beginning. Let's say these ones here. Copy everything. Oh, now it's still being malformed, right? So now already we were able to remove a couple of statements while still triggering the bug. So we'll also save now. And again, try a couple of statements that we can remove. Still malformed. Again, we succeeded. Let's take some more. Still malformed, great. So now already the test case fits on a single file. Let's see if we can remove the pragmas, the options here, by still being able to trigger the bug. Okay, no, so actually it seems some of those were actually responsible. I speculate now that the encoding perhaps is necessary. So copying again. Yeah, so actually like we'll need this encoding pragma here. Let's try some other ones. These three statements here. Yeah, still malformed. Okay, this didn't work. What about these ones here? Also didn't work. These ones here. Okay, still malformed. That worked. What about these ones? Here we have to undo this. But you can already see where this is going, right? We can continue doing this kind of step. We could also do it in more systematic ways. There are actually some well-established algorithms to do this, for example, delta debugging. But we'll just repeat this until we have a minimal bug-inducing test case, and then we can further debug this test case, analyze it, and, for example, report to developers or directly fix it. Great. For completeness, I also want to briefly check some of these other bugs that we found. So let's see what else we've got. Seems actually this is the only one that we found now. So what we now can do is, because we actually found a bug that triggered the JVM, so now we can actually try to figure out, although sometimes this might be quite difficult. Right, so which thread caused the crash? So this was the Java thread database 10. Right, so we basically can look into the logs directory and try to find the thread 10. And now the JVM didn't cleanly exit, which means that we don't have this test case without the suffix, right? And here, basically in this file, we have both the statements for creating the database state, as well typically a lot of select statements, but here actually we only have a couple of them, right? So actually we can try just to take all of them and execute and see whether we can cause this crash here in SQLite. So I copied this. Now let's execute SQLite again. Paste everything. Oh yeah, and actually we can see a segmentation fault. Right, so here we now crashed the JVM. Likely only the last SQL statement is necessary to trigger this, so we can try to reduce all the other SQL statements, copy everything, execute SQLite again, and still we can see the segmentation fault. I'm curious, can we actually just remove all of them? Sometimes that's the case. Okay, not the case, but now already know how you could further reduce the bug manually. And in one of the other videos, we'll also cover how we can do this automatically. Great. So with that, thanks for listening again, and see you in the other videos.